I want to welcome now Professor Martin Spindler from Hamburg University and Dr. Heinrich Kögel from Economic AI. You will talk about optimizing the customer journey with Causal AI. You are, as I mentioned, professor for statistics, data science, and machine learning in Hamburg, and you are focusing particularly on the combination of machine learning and causal inference. And next to that, you also founded Economic AI, where Heinrich, you are working as a data science manager. So the stage is yours. Enjoy your time.
Thank you very much for the kind introduction. Before we start, maybe Heinrich and I are afterwards going back by train to Munich and Hamburg, but after the previous talk, I'm confident that we'll be in time, yes. Hopefully. So our topic is optimizing the customer journey with Causal AI. I will give some background. What is Causal AI? What is causal machine learning? And Heinrich will then dive into a real-world application. So part one, introduction. Before we get started, maybe a question to the audience. Who of you have heard about causal machine learning, causal AI? 2, 3, some, but not many. So therefore, we start first with an introduction. What is causal machine learning about? On the one hand, we have AI. And AI is very strong in learning patterns in complex data, but it's correlation-based. And what usually done with AI is making prediction, making forecasts. And all these successful applications, like image recognition, in big data, you learn complex patterns and then use this to make predictions. On the other hand, we have causal inference, or the question for why, because often we are interested in understanding mechanisms, and for this, there's a field of causal inference, so we have to go beyond correlation to understand the mechanism. And so pioneers like Judea Pearl, Rubins, Imbens, who won the Nobel Prize 2 years ago, have worked or developed models, and this is really completely unrelated to AI. The question is, given our data, can we learn causal effects? And now, this is causal inference, and now we often have complex data, high-dimensional data, and now we would like to use AI in our causal models. And this leads to this new field of causal machine learning or causal AI. Maybe this sounds now very abstract, but maybe I usually use a very simple example to make the point. And this is famous lighter lung cancer example. So assume we find a positive correlation between a lighter with you and lung cancer. So this means people who wear lighter with them will have this higher probability lung cancer. And of course, this is a correlation. And we all know, also we are not medical doctors, that wearing a lighter does not cause lung cancer. The true causal model is not much complicated, but we omitted smoking. So smoking, this is established in the medical literature, induces or causes lung cancer. And smoker wear a lighter with them. So this is a true causal model. And somehow we have not understood this. And now the interesting part is prediction models still might work, because if wearing a lighter and smoking is highly correlated, the information that you wear a lighter with you is predictive for if you will have lung cancer. So a prediction model still could work. And this is what machine learning does. It uses correlations to build a prediction model. But now where is the problem? The problem is if we want to intervene or change something. So for example, the health minister of this country hears about this, and she wants to intervene and want to reduce lung cancer rates. And then he or she might come up with the idea to forbid lighters. But this won't work. People will switch to matches. And here's the reason is that we have not understand the causal mechanism, but if we want to intervene, change something, we need to understand the causal relationships. And there are many problems here. Another point to make the difference between standard machine learning and causal machine learning. Typical example, customer churn. We would like to predict if a customer churns. This is a prediction problem. But the more interesting question is, if we have identified a customer who will leave, how can we retain this customer? Shall we send a voucher? Shall we do a call? So these are causal questions because we want to intervene, we want to take action, and then see what is the effect on the outcome. Or if we want to find out what are the causes why this customer leaves. And this goes far beyond what standard machine learning AI does, which is only correlation-based. And here I brought not an exclusive list, but some applications which are typical causal problems. One is resource allocation, if you want to decide in which marketing channels you should spend your budget. Dynamic pricing is an important example. Targeted marketing. Customer journey. Heinrich will then later present a case study where we show how this causal machine learning, causal AI can be used for customer journey improvement. And another example I've not listed, where we've worked recently on is, for example, production optimization. So how you can use causal models to improve production processes. And maybe some of you who followed this, causal machine learning AI has become in the last years a quite hot topic in industry. So it started with Amazon, Microsoft, these tech companies went fully into causal machine learning because the problems they have, like marketing optimization, are causal problems. But we see that this idea picked up in the industry. So Spotify, Netflix built up big teams for doing causal machine learning. And in Germany also Zalando goes into this direction. And my prediction would be that all companies, small one, middle-sized one, which try to apply machine learning in the long run will come to causal machine learning because standard machine learning does not solve many interesting problems. And as a research field, it's also a quite new field. So causal inference has a long tradition in economics, in medicine, and the field of combining causal inference with machine learning is quite recent. So one of the founders of economic AI, Professor Chernosuke from MIT, he had some path-breaking work where he developed methods where we can use machine learning to do really causal inference. And so here it's a very active field which is now booming. So there are other topics besides generative AI which are important. And the interesting part is what causal machine learning does, generative AI cannot solve. So in this thing we are safe for some time. So now, if you have a causal problem, what can you do? How can you attack this problem? And there is a big toolbox what we can do. One big toolbox is A/B testing experimentation. Nothing new in physics, medicine. If you want to learn something, you do a controlled experiment. Nothing new. Also, the statistics is not new. But we see here an interesting development that you can use machine learning methods AI to better evaluate A/B tests. And I will later show what's the innovation here. Another point is often we cannot do an experiment because there are ethical reasons, there are cost constraints, and then we have so-called observational data which are somehow given. And then the question is, can we learn also causal effects in this kind of data? And there are tools like regression discontinuity, IV, which have been developed under the umbrella of structural economic models. When given observational data, we can try to uncover causal effects. And this often in pricing, when you don't want to do an experiment, you want from your given data extract elasticities. And then there are hybrid methods which combine both worlds. I will omit. But now the idea is these are classical methods from causal inference, and now we combine this with machine learning method, which makes some additional theoretical problems which have been overcome in recent research. Here, as I said, A/B tests is now in a digitalized world a big topic because it's so easy to conduct experiments. As I said, A/B test, it's simple comparison of mean, but there are some problems. With A/B tests, we can, if we do A/B tests and use machine learning, we might get a higher precision of our estimates. So if we include additional covariates, our estimates might get more precise. This is one innovation. And another innovation, probably the most important one I will present on this slide. One, from my point of view, one of the biggest innovation in theory, but now arrives in industry, are so-called heterogeneous treatment effects. This sounds quite academic, but it's highly relevant for practical applications. Because in the standard models, you assume you have a marketing campaign, and this marketing campaign has the same effect for each individual. But of course, this is not true. A marketing campaign can have a different effect for men and women, depending on the age, if you live in a rural area or not, or even the interaction of all of these things. So this pattern, this heterogeneous treatment effects, can be a very complex pattern. And now we can use machine learning methods in experiments or in observational data to learn these heterogeneous treatment effects. And if we have estimated this, it's the second step, we can do policy optimization. Because if you know how each individual reacts to a certain marketing campaign, we can for each individual then decide what is the best for you, which one shall we present to this individual. And we see that this is very booming. And so in research, you call it heterogeneous treatment effect, which sounds boring, but personalized medicine or personalized marketing or targeted marketing, dynamic pricing, nothing else than heterogeneous treatment effects. You assume that the treatment effects varies on some covariates, and we would like to figure out this pattern. Okay, this was a short introduction. What is causal machine learning about? So, of course, some technical points. I will give later also some references for those who want a little bit to dive more into it. But now I pass to Heinrich for the use case.
Yes, perfect. Thank you, Martin. And so now that we talked a little bit about causal machine learning and maybe also touched a little bit on double machine learning, a software package that we developed. Next, let's have a look at a use case where we leverage the double machine learning approach. So a causal machine learning approach. And So what happened in this project is we're approached by a car manufacturer that is active around the globe and that recently started to sell their cars online. And the way how they sell their cars online is they have a platform. And on this platform, people can browse through a list of cars that have already been produced. And if a person then wants to buy one of these cars, they can first make a reservation for this car. And then in the next step, they can actually buy it online. So this is how this platform works. And let me tell you, this platform looks really nice. However, at the time when we were approached by this manufacturer, there was only one problem with this platform, which was that unfortunately only very few people interacted with the platform. And even fewer actually made car reservations, not to mention buying any car at all. And so what this car manufacturer then did to try and improve user engagement was they ran a number of simple A/B tests where they tried to optimize the layout of the platform. But this was not really successful. And for this reason, they then approached us and asked us if we could help them develop a strategy to improve engagement. And what we then did was we sat together with this car manufacturer and brainstormed ideas how we could improve engagement. And the idea that we then came up with was that we would create different personalized versions of the platform where people would see different pre-selected types of car models when they enter the platform, depending on their observable characteristics. And in particular, we created 3 different platform versions. So when people accessed this platform, they saw either a range of more affordable cars, so this was the first version, or a selection of mid-range cars, or a range of expensive cars. And the idea behind this approach was that maybe there are certain groups of people that would prefer one of these 3 price ranges of cars, and that by showing them immediately a pre-selection of such cars, that they might become more likely to interact with the platform and hopefully also reserve and buy a car. So this was the idea, and now to be able to implement this approach, what we needed to do was to create a set of decision rules that would tell us which platform version to show to which group of people. And the characteristics that we had available to create these decision rules were mostly characteristics related to the technical devices that people used. So, for example, we knew if a person used a mobile device, a desktop computer, or a tablet to enter the platform. And in addition to this, we also had some basic geographic information available and information about the time when a person accessed the platform. So, for example, the time of the day or the day of the week. This was the idea now. We would create different decision rules to decide which platform version to show to which group of people. But how could we now do this? And so for this, we decided to run another A/B test where we showed the different platform versions randomly to the visitors of the site, and then to measure how the visitors react to these different platform versions, we defined a number of KPIs, such as the time that users spent on the platform, the number of cars that they viewed in detail, and of course, we also looked at the share of users that make car reservations. And so once this A/B test was then finished, what we did was we conducted a so-called heterogeneity analysis. So going back to the heterogeneous treatment effects, heterogeneity analysis using double machine learning, which allowed us to identify in great detail certain groups of people that responded particularly strongly to one of these 3 platform versions. And this was actually quite interesting. So, for example, we found that the share of, that the engagement of Apple users that accessed the platform in the afternoon on the weekend, that their engagement was particularly strong when we showed them the platform version that initially displayed only expensive cars. Based on the results of this analysis, we were then able to derive a diverse set of decision rules for our personalization strategy. And what we then did in the last step was we conducted a so-called counterfactual analysis, which allowed us to assess how the KPIs in our experiment, how they would have changed if all of the people in the A/B test would have been exposed to that sort of optimal version of the platform. And what we found there was that actually our personalization strategy leads to a considerable improvement in user engagement. So, for example, we found that the time that users spend on the platform, that this increases by about 16%, and that the share of visitors that make car reservations, that this share increases by around 9%. Yeah, and our car manufacturer was actually quite happy with these results, and we were even more pleased that they recently actually started to implement this approach on their platform. Yeah, cool. So this was one example use case of where we leveraged the double machine learning approach. But of course, there are also many other areas where we can use double machine learning. So, for example, we can use it in pricing to estimate valid price elasticities, or we can use it in resource allocation to determine how to optimally allocate our budget, and many other areas. Maybe one could even say everywhere where causality matters. And back to you, Martin.
Well, thank you very much, Heinrich, for the presentation of the use case. So now at the end, I want to give you some references where you can get started. At the beginning, I motivated what is causal machine learning, causal AI, very generally. Double machine learning, Heinrich mentioned, is one specific approach. This allows us to do causal inference when we use machine learning methods to estimate parts of our model. Because this is not trivial, so that you get the right estimates, because machine learning methods, for those of you who are more in detail, usually introduce some kind of biases. Our estimates we get with machine learning methods are usually biased, and this double machine learning allows us to estimate unbiased effects from the data. And what are resources? So we have the WML open source package, where you can go to the starting page, where we have big example galleries. We also have some introductions. I think this is a good starting point. If you want also a little bit understand the theoretical foundations, so the first one is a reference, it's somehow the white paper for double machine learning, which is very technical paper. Maybe to get started, it's easier to start with our documentations for the package, which are some kind of easy introduction. And we're also working on a textbook to make these methods more accessible, because in some point, it's also a little bit technical how to get the inference right in this field. If you're more interested in application, so this was more for people with background in machine learning and for the data scientists. If you're more interested on a high level on these things, now if I say can recommend, it's a little bit biased. We had an article in FAZ, a very light introduction on causal machine learning, what it is, why it's important. We have an article in a marketing journal, in an applied marketing journal, where we describe a use case from dynamic pricing for a ride-sharing company. So this is good introduction. And the middle one, it's a project with Novartis, where we developed a system where now the resource allocation is done in a data-driven way. And also we describe in this paper the technical side. There was another book chapter with Novartis where this described how to implement such models in organizational wide. Because one point is doing the modeling right, but to get it in an organization, you of course need the data, you need cultural change, so it's much more complex. But it was for us nice to see such a larger project which has a big impact, which also does not only the modeling part, but contains more sections. And not listed here, for those maybe interested in production optimization, we have a project with Osram. We used causal machine learning, policy learning to derive better policies when to do rework. And for this also now a paper recently was published at Journal of Machine Learning Proceedings. And if you cannot access them, I'm not sure if all are freely available, you can reach out to us and we can send you, of course, the articles, because some might be behind a paywall. Some are, I think, open source, but not also, not 100% sure. For data scientists, if you want to learn about this, we also designed now training, 2-day training in October, November, which is open to data scientists from industry. So in the past, we did this for companies, but not all companies have so many data sets that they can do one course. So this is really to bring these methods into practice, and hopefully it's widely applied even more than it's currently done. So this was already, I think, perfect in time, but it's always 0 minutes. Yes. So thanks a lot for your attention, and I'm happy for any questions or comments.
Yes, thank you, Martin. Thank you, Heinrich. We have some room for questions.
Unfortunately, we can't say.
A big one.
But it was big. Yeah.
It was worth a try.
Yeah. So this were around. So I can't talk about like it's in super detail, but I think it was around 40,000 sessions that we used.
But maybe only to add, this is the advantage of this using A/B tests with machine learning, because in classical A/B test, you could, of course, do tests for subgroups. But the problem is, in beforehand, you have to design, I want to have an effect for men and women, I want to have according to age, and then you have if you have many variables which could potentially matter, you have so many subgroups, and then you don't have this kind of observations. And this is now the good thing. You conduct an experiment, and then ex post, you can use machine learning to identify different subgroups, and therefore you need much less data than you would need in a classical standard A/B test, where you, in the protocol before, you need to specify what groups you're looking after. And this, I think, is a big advantage, that we don't do this. We ex post can analyze this, and then we need smaller data than we would need for a full A/B test in advance.
More questions? If not, then thank you again